Alright, so here we are with lesson 4, and we're going to start off again with a warm-up. And so we're going to do some derivatives again. The derivative of sine is, the derivative of sine y prime equals cosine x. The derivative of cosine is y prime equals negative sine x. The derivative of tangent y prime equals secant squared x. The derivative of cosecant is negative cosecant x, and cotangent x. And the derivative of secant x is secant x, tangent x. And the derivative of cotangent is y prime equals forgot my negative in there. Throw a little negative. Oops, come on. There we go. Throw a negative in there. Negative cosecant squared x. All right. All right. So the next part says to use your calculator to. Come on. Next part says to use your calculator to determine on what interval y equals ln of x minus x squared is increasing on the interval from 0 to 2, and it does say use your calculator here. So since let's see, we've done a bunch of these together, but I'm going to pause for a minute and pull up my calculator. I'll let you do the same thing. So okay, so here we are. I've got my equation punched in. You can see y equals ln of x minus x squared. And because we're working on the interval from 0 to 2, I'm just going to go to the window right here, and I'm going to set my x min at 0. My x max I'm going to set at 2. And let's see here. I need to know about my y min and my y max. You know what? I'm just going to graph it and see what it looks like here. Oh, look at that. Okay, so I've got the whole thing from 0 to 2 here, and I'm supposed to determine on what interval we are increasing, which means I need to know where the max is, and it looks to me like there's a max somewhere in this area between 0 and 1. So I'm going to go up here to my second calculate button, and I'm going to say, let's see, we're doing a max here, so we're going to do number 4 for the max. It's going to ask me for a left bound, so I'm going to scroll way over to the left side here. I know I'm on the downside there. Give me a right bound, so I'm watching my y values to see when they start going down again. It looks like right about there. And then this time I'm actually going to take a guess. Normally I wouldn't do this, but I'm thinking the estimate somewhere in there. And there we go. Looks like we have a maximum at x equals 0.707 and y equals negative 0.846. All right. So if I go back to my picture here, I could actually draw this thing. Here's my x and y axis here. Alright, so here's x. We'll put 2 over here. We'll put 1 right here. And this is my y axis. And this graph is doing, I don't know, it was doing something like this. There we go. Not perfect, but close enough, right? So we had a max right about here. And that point was, excuse me, 0.707. And the y part of that, which I don't even think we really need to answer this question, was like 0.8. I don't remember, but to answer the question, I really don't even need it. So I'm just going to put y right there. So we are increasing, so y is increasing on the interval from 0 to 0.707. All right, that's all they were really asking for there. We could also do this by hand, but you know, and I would encourage you to do it by hand by taking the derivative, setting the derivative equal to 0, looking for your critical points and that kind of thing. Good exercise in doing that. But since it said to use our calculator, we're just going to leave it there for today. All right. So here we go. So we are looking at, slide this over just a little bit. So we are looking at integrals again today, and excuse me. So our trigonometric antiderivatives, we want to know these. And so we're going to start off by doing these. The integral of sine x is negative cosine. Come on. This is not working well for some reason here, and I don't know why. All right, let's try this again. So this would be negative, come on, negative cosine x plus c. The integral of cosine x is sine of x plus c. The integral of secant squared x is tangent of x plus c. The integral of cosecant squared is negative the cotangent of x plus c, and the integral of secant tangent is secant x plus c, and it looks like we have one more down at the bottom there. Let me see if I can grab this one, scroll just a little bit here. Alright, and the integral of cosecant cotangent is negative cosecant x plus c. Okay, so those are our trigonometric antiderivatives. And so again, we're going to look today at taking the integral of trig functions. So we're going to start out with y equals sine of 8x. We know that y prime, so I would take the derivative of sine of 8x. So that would be cosine of 8x. And then I would also multiply that by the derivative of the inside material, so that would be times 8. Okay. Likewise, if you were to take the integral of cosine of 8x, that means that I should get sine of x back, just like on the left side over here. If we take the integral of sine x, we know that's going to be negative cosine x. If we take the integral of cosine x, we know that's going to be positive sine x. So on the right side here, when I go to take the integral of cosine of 8x, I know that it had to come from sine of 8x. All right, but if you were to take the derivative of sine of 8x as we saw over here, we would also have a times 8 on the right side or on the left side. It doesn't really matter. So if I were to take the integral of this or the derivative of this sine of 8x, I would have an 8 being multiplied here. So I'm going to need to divide by 8, just like we did with our exponents on our variables, and plus c. And again, you can check this very easily. If you take the derivative of sine of 8x, you would get cosine of 8x times 8, and then the 8's would cancel out, and you're done. All right? If we take the derivative of tangent of 6x, that would be secant squared of 6x, and then we would take the derivative of the inside material. So again, we have that times 6 on the outside there. So if we take the integral of secant squared, we know that the integral of secant squared is tangent. So that's going to be tangent of 6x. But if I take the derivative of tangent, again, I would have that 6 out there, so I would need to divide by 6 here, plus c. All right? Likewise, y equals secant of 13x. So I take the derivative of that. The derivative of secant is secant 13x times tangent of 13x times the derivative of the inside, which is 13. So hopefully you can kind of see what's coming up here. If I take the integral of secant 13x tangent 13x, this is going to be secant of 13x, but if you were to take the integral of that, you would have, or the derivative, you would have 13 on the outside, so I need to divide by 13 here in order for those to cancel each other out, plus c. All right? Hopefully this is making sense as we go through these. Let's see, next one, sine of x squared. So now we have the derivative of sine of x squared would be cosine of x squared. And then we would take the derivative of the inside, which is times 2x. So I come over here, and you can see that now I'm taking the integral of 2x cosine of x squared. And so again, what I'm asking myself is what derivative gives cosine? Now, we could do this with a u substitution just like we did before, but we don't really need to here, because I know that the antiderivative of cosine is sine, and I know that if I take the derivative of sine, that's cosine. So I know this is going to have to be sine of x squared. Now, do I need to divide by anything? Well, in this case, you don't, because if I take the derivative of sine of x squared, as you just saw over here, we get cosine of x squared times 2x. This 2x right here is the derivative of x squared. So the derivative portion of the inside material is already part of the integral, and I don't have to worry about it. All right, plus c. Tangent of x cubed. All right, so the derivative of tangent is secant squared of x cubed times the derivative of the inside, so that would be times 3x squared. Now, look over here on the right. I want to take the integral. If you notice, I have the integral. I've got secant squared x cubed. Okay, so the first question I want to ask myself is, what is the antiderivative of that? Well, the antiderivative of secant squared is tangent squared, or tangent, excuse me. So I know I'm going to have tangent of x cubed. All right. Now, if I take the derivative of tangent of x cubed, not only do I get tangent of, or secant squared of x cubed, I get 3x squared. The x squared's already in my integral, so I don't need to worry about that. But if I took the derivative of this inside part, I would have a 3 sitting out front here. So again, I need to divide by 3 in order to get that 3 to cancel out in this case, plus c. All right, let's keep going. We got one more here. So the derivative of cosine x to the fourth, the derivative of cosine is negative sine x to the fourth times the derivative of the inside material, which would be 4x cubed. We go over to the right, and I want to take the integral of sine of x to the fourth. Now, here we go. I got a problem here. Okay? I've got a major problem here, because number one, I know that the antiderivative of sine, okay, so the integral of sine of x to the fourth would have to be cosine of x to the fourth, and it would have to be negative, okay? So that part I can see. But if that's my function and I take the derivative of this, of negative cosine x to the fourth, look at what I get. So if this is y equals, okay, so let's call this, that's y equals right there. So if I think that's my integral, or my antiderivative, and we should put a plus c over here, then if I take the derivative of that, y prime, you can already see, first of all, the derivative of cosine is negative sine, so the negative here and the negative sign would cancel each other out, and that would give me sine of x to the fourth. But I would also have to take the derivative of the inside material here, which is 4x cubed. Now, the problem is, you cannot manufacture a variable. You can't just say, oh, well, then I'm going to divide this. I'm going to take this and divide this by, 4x cubed. You can't do that. Okay? That doesn't work. Dividing by a number is different from dividing by a variable. So I can't just divide out an x cubed. Okay? I need to, when you take the integral, you need to be able to see the derivative of the variable in the integral. Like when I took the derivative, or the antiderivative of secant squared x cubed, I know that the antiderivative is tangent of x cubed. Okay, I saw the integral, the derivative of x cubed right next to secant. So that was already taken care of for me. I didn't need to worry about that. I cannot do this down here. I cannot manufacture variables in my integral. That's a big old no-no right there. Okay? So you just want to keep that in mind as we go through this. All right. Okay, so let's scroll down to the next page and see what we got. Looks like we have a blank page here. Here we go. All right. So we have, all right, the integral of 5 cosine 5x So the first thing I'm going to do is look at cosine of 5x. What's the antiderivative of that? Well, that would have to be sine of 5x. All right. And if I look at that, the derivative of sine of 5x would be cosine of 5x times 5, which I already see in the integral, so I just need plus c. Pretty straightforward on that one. Okay, so for my next one, I'm going to rewrite this guy here. I'm going to rewrite this as the integral of sine of x. And I'm going to bring the cosine squared up, and I'm also going to rewrite it a little bit differently. I'm going to write it, instead of cosine squared, I'm going to write it as cosine of x. And since I'm bringing it up from the denominator, I'm going to put the negative 2, right like that. Now, again, all I did was, instead of writing the squared next to the cosine, I put it on the outside. Those two things mean the same thing here. Okay, so now what I've got is I've got sine of x times cosine of x to the negative 2, and I'm going to do some u substitution here. So I'm going to let u equal cosine of x. I'm going to take the derivative of both sides. That's du equals negative sine x, and dx. I'll divide the negative sine x out on both sides, so that's du over negative sine x equals dx. All right, and now I'm ready to substitute back in. So what I have is the integral of sine of x. All right, so that was my original statement there. I'm going to replace cosine x with u, so this is u to the negative second power, and then I'm going to replace dx with du over negative sine x. All right, so we can see some canceling is going to go on here again, so we're going to cancel out the sine x's. Those are going to go away, but I have a negative 1 left in the denominator here, so I need to take care of that along the way here. So I'll rewrite this one more time. I've got the integral of u, and I'm going to bring the negative up, so that's negative u to the negative second power times du, and then I'll take the antiderivative of u to the negative 2, so that's going to be u, and I need to, well, I've got the negative in front, but I need to add 1 to that, so that's going to be negative 1, and then I need to divide by negative 1, remember my exponent, plus c. Now, the negative in the front and the negative 1 are going to cancel each other out, so all I really have is u to the negative 1 plus c. And so replacing u with cosine of x, I get cosine of x to the negative first power plus c, and I could also write that as 1 over cosine of x plus c. All right, so on a multiple choice test, you'd be looking for this bottom answer. On a free response, you could just leave the top one and you'd be fine with that. All right, okay, let's keep going here. All right, next one here. Okay, so I see a sine squared in here, and I see a cosine of 3x. Here's the thing. When I look at this problem, I see this. This is the derivative of sine 3x. Now, don't get me wrong, this is sine squared, you're right. But when I take the derivative of sine squared of 3x, I'm going to end up with cosine of 3x as the derivative at some point. Okay, so hopefully that kind of makes sense here. But so I'm going to actually start by looking at sine squared 3x. Okay, so I need to know, let's see here, how do we want to do this one? So we're going to let's do a u sub on this one again. All right, so we'll let u equal sine of 3x. Okay, because remember, this is really sine of 3x to the second power, the whole thing raised to the second power, just like on our last one. So taking the derivative, du equals cosine of 3x times the derivative of the inside material, so that would be times 3 dx. We want to divide out the cosine on both sides, so we're going to have du over 3 cosine 3x equals dx. Now we'll substitute it back into the original function, so we need to be careful when we do this. So here we go, original function. My original function was the integral of 3. Now remember, my u value is sine, so that's going to be u squared. My cosine of 3x is still in there, cosine of 3x. All right, and I'm going to replace dx with du over 3 cosine 3x. All right, and this time we've got a lot of stuff to cancel. So the cosine 3x's cancel here, the 3's here and here cancel. So all I have left is the integral of u squared times du. The integral of u squared is u cubed over 3 plus c. And since u was equal to sine 3x, I know that this is going to be sine. Oops. Erase a little bit here. Oh, come on. There we go. So this is going to be sine of 3x. I'm going to write this 2 different ways here. To the 3rd power divided by 3 plus c. Or you could also write this as sine cubed of 3x all over 3 plus c. Either one of those would be a valid answer, valid solution. All right. And again, I would encourage you at any time to turn off the video and try one of these on your own. We've got one left here. So again, I'm looking at sine of 11x being a partial derivative of cosine squared 11x. All right. So I know that this function is going to have to start off with cosine squared 11x. Why do I know that? I'm just thinking out loud here. I see that, well, let's just look at it. If I take cosine squared of 11x, okay, and actually I'm going to write that a little bit differently. So cosine of 11x squared. So let's say I thought that that was my antiderivative right there. Now, if you look at this, if I take the derivative of this, okay, so I'm just talking out loud here. If I take the derivative of this, the 2 would come down in the front. Okay, so I'd have 2 times cosine of what do we have here? Of 11x. Sorry about that. And so we'd have that left. Oh, you know what? I knew something wasn't right here. This would have to be, if I thought that was my derivative. I forgot to add 1 to my variable there. So, all right. So this would be a 3 in front. That's what wasn't making sense to me here a second ago. So this would be 3 cosine of 11x to the, and this would all now be squared, because again I would be subtracting 1 from the exponent. Then multiplying that by the derivative of the inside, so I'd have to take the derivative of cosine 11x, which is sine 11x. And then the derivative of that inside material will be times 11. So you can see that I'm close, but I'm not quite there. What you see extra is here is you see the numbers 3 and 11 as extras. Well, just like before, if I go back up to my antiderivative here, that 3 that's my exponent, I don't see that in the integral, so I have to divide by that. I need to divide by 3. I'm also going to end up with this 11 in my derivative, so I'm going to have to divide by 11. All right? So if it's just numbers that are missing, I can put those in the divisor, or I can, if this was a fraction up here, I could flip and multiply. But again, I would encourage you to do this with a u substitution on your own and see, what you get from that, and see that you can get cosine of 11x to the 3rd power and over 3 times 11 plus c. It should be a simple u substitution, just like we did on the left side here. So use this guy on the left as your guide and see that you can come up with that, if what I did doesn't make sense. Okay? If you can manufacture this in your head, then you're okay. All right? And let's see. You know what else? I missed one thing under here. What's the derivative of cosine, everybody? It's negative sine. So I need a negative 3 under here. You know that? Boom. Now I'm done. Okay? So again, try it with a U substitution. See where you get. Have fun with that one.